Hi guys, and welcome back to Elevate Chem. I'm Jesse, and this is the walkthrough for the 2014 VCAA chemistry exam. And in this video, we'll be looking at the multiple choice questions 21 through to 30. So let's get into it. Question 21 states that maltotriose is a trisaccharide that is formed from 3 glucose molecules linked together. The molar mass of glucose, C6H12O6, is given there, and we need to work out the molar mass of maltotriose. So maltotriose is 3 glucose molecules linked together, so I can draw it something like this. Of course, this is a very, very crude diagram. Now, one of the ways you might be attempting to solve this question is by thinking that 3 times the 180, because there's 3 glucose monomers, and that would give you 540 grams per mole. However, when these glucose molecules react and link together, each of these little bonds actually spits out a water molecule. And that means that is a decrease in this value here. It's not actually the full 540. Instead, it's 540 minus 2 times the molecular mass of water, which is 18. So it's 540 minus 36 equals 504 grams per mole, which gives us answer C. The formula for that, in case you're interested, guys, is the moles, or the number of glucose monomers, and then the amount of water that you're going to remove is N minus 1 H2O molecules. Awesome. Moving on to question 22. The general formula for a triglyceride is given right here, and we're looking for which equation represents the hydrolysis of a triglyceride. Now, the hydrolysis is the addition of water. Unfortunately, that doesn't really help us out for this question, as every single answer has 3 water molecules added to it. Now, the easiest way to do this question is if you happen to have memorized the fact that this answer A is the correct answer, and that's what a hydrolysis of a triglyceride looks like. The reason why is because you're left with this glycerol molecule, which has 3 hydroxy groups, and you're left with 3 acids left over. Another way actually of looking at this question was to actually do an elemental balance. And you can see on the left hand side here that I should have 6 oxygens plus the 3 here. I should have 9 oxygens in total. When I look at my right hand side, I get 2 times 3, which is 6, plus the 3, that gets me 9. If I move to some of the other options, that actually isn't true. I have 6 oxygens here plus an additional 3, that makes 9. And in this answer, I only have 6 oxygens, so it can't be that. Similar situation happens here, 6, I only have 3. Well, actually I have 6 over here, but there's 9 there. And in this option, I have 9, and again, I only have 6 oxygens. So actually one of the easiest ways to work this out, if you weren't sure entirely what it was, or if you haven't had it memorized, you could have done a balance and have seen that there was more oxygens on the left-hand side of the reaction for all 3 of these, cancelling them out. And that means that A was the only available option. Moving on to question 23. There's a lot of text here, guys, so I'm going to jump to this actual question component. The amount of energy released by the complete combustion of methane extraction from 1 kilogram sample of methane hydrate at SLC is ... So I'm going to need to understand what methane hydrate is. It's given to us right here. Here's the formula. And we need to know the energy released. So one of the things that we're going to need to know is, well, how much energy is released from the combustion of methane in general. That's given in your formula sheet, guys, as the combustion enthalpy, and that's given as delta HE of CH4 is equal to negative 889 kilojoules per mole. And the negative indicates that there is energy released, so I'm actually going to end up with a positive number. Now we're looking for combustion of methane from a 1 kilo sample of this methane hydrate. So that means I'm going to need to work out the moles of methane hydrate. So moles of methane hydrate is equal to my mass divided by my molar mass, which is 1 by 10 to the 3, converting kilograms into grams. And the molar mass can be found to be 16 plus 6 times 18. So essentially what I've done here, methane component is 16 and then 6 times the 18 to account for the water. And that gives me the total moles for the methane hydrate as being 1 8.06 moles. Now, how do we work out the number of moles of methane within that sample? Well, if we have a look at it, methane hydrate contains only one methane molecule. And that means that there's a one-to-one relationship between the amount of methane obtainable from the methane hydrate. So that means moles of CH4 also equals 8.06, and therefore delta H E CH4 total equals 889 times 8.06, and that is equal to 7.17 by 10 to the 3 kilojoules, which gives us answer B. Question 24. Again, my go-to method, skip the text, read the question. Methane is a renewable energy source when it is obtained from natural gas, coal seam gas, methane hydrate, microbial decomposition. This is going to be one of those things that you just need to remember, guys. You could also treat it as potentially a general knowledge question. Which one of those is a renewable energy source? When it talks about renewable, it means in the relatively short term or readily replenishable. Natural gas, coal seam, and methane hydrate, none of those are readily replenishable, whereas microbial decomposition certainly is. On to question 25. Considering the following information, again, I'm going to skip it for now. Where would the following reaction be placed in the electrochemical series if the above tests were carried out under standard conditions? So I've got this reaction here, and we can see that overall it's a reduction because I'm gaining electrons. And if reduction is taking place, that means my rubidium 2+ is actually acting as an oxidant. Now, if that's the case, we know that it will react with reductants that are lower on the electrochemical series. So we can see that these two situations here are where reactions actually occur, and that means that both of those, both the nickel and the copper, are lower on the electrochemical series. However, the rubidium 2+ won't react with things higher in the electrochemical series, which means that both our silver and iron are actually higher. Now, filling in those values, the E0 for all of those species, not the rubidium, but actually for the copper, the iron, the nickel, and the silver respectively, is 0.8, 0.77. For the copper, it's 0.34, and for the nickel, it is negative 0.23. So we know that rubidium must be sitting between the copper and the iron because it didn't react with the iron and it did react with the copper. That means it must be sitting between the 0.77 and 0.34. As I said, guys, the rubidium is an oxidant and so will react with reductants that are lower and won't react with reductants that are higher. Moving on to question 26. Consider the following experiments. Going to skip that for now. It would be predicted the reaction will occur in which of the following options. So we've got three options here, and we're going to need to use the electrochemical series in order to work this out. So in beaker 1, we've got an oxidant, Ag+, and the reductant is the solid nickel. If we have a look at the electrochemical series, we can predict that a reaction will occur, and the reason why is the oxidant, the Ag+, is higher than the electrochemical series, the nickel solid, the reductant. So that means beaker 1, there's definitely a reaction that's going to occur. In beaker 2, the oxidant is going to be Cu2+, and the reductant is I-. Again, I'm grabbing this information from the electrochemical series, guys, and because of that, the reductant in this case is actually higher, and that means no reaction will occur. In beaker 3, this was a little bit of a tricky one, guys. Not only did we have chlorine gas present, but we actually had both the potassium and the iodine present. So if you have a look at that, because we've got both the potassium and the iodine, because we have the iodine available as a reductant and it's lower on the electrochemical series than the oxidant, the Cl2 gas, that means the reaction can occur. If you only considered the potassium, you would have incorrectly said that this wasn't possible, but it was due to the presence of that iodine. So both beakers 1 and 3 expected to have a reaction, in which case the answer is C. Moving on to question 27. Now you could have used the electrochemical series for this, and at some point you definitely did need to. However, you could actually knock out 2 of the answers by using a little bit of logic. Looking at option D, it says electrons in the external circuit will flow from the silver electrode to the zinc electrode. Now electrons always flow from the negative to positive terminal, at least in galvanic cells. So that means the zinc electrode must be the cathode, and that would indicate the silver electrode is the anode. Now if this was the case, both A and D would be correct, and multiple choice questions, unless specified, only have one correct answer. So that means neither D or A could be correct based upon that sort of logic just there. So look at my options B and C. Well, I just worked out the silver electrode can't be the anode, which means the silver electrode must be the cathode, and conversely, the zinc electrode is the anode. And if the zinc electrode is the anode, that means oxidation is occurring, and oxidation is the loss of electrons. So we're going to be going from Zn solid to Zn2 plus aqu plus 2E minus. And again, the reason why I know this is because the zinc electrode is the anode, oxidation's occurring. That means I'm producing this Zn2 plus, and that means the concentration of Zn2 plus ions will increase, giving me answer B there for question 27. For question 28, what should be observed as at the zinc cell as the cell discharges? So I don't need to read any of the rest of the question. I can base it purely upon the information that I found here. And I worked out that the zinc electrode was the anode, and at the anode, what's going to happen is my Zn solid is actually going to turn into my zinc aqueous. So what's going to happen to the electrode is it's going to become thinner and pitted. As this reaction proceeds, guys, the zinc solid is actually going to dissolve out into the solution, and that means the electrode itself will become thinner and pitted. Moving on to question 29. A hydrogen oxygen fuel cell uses this many moles of hydrogen gas per second of operation. The current produced by this cell is. So for current questions, the equation that I'm going to be using is Q equals IT, which I can rearrange to give I equals Q on T. And the other equation that I have for Q is Q equals moles of electrons times Faraday's constant, which is given in our data booklet. So I'm going to start off by working out the moles of electrons. So I've got the moles of hydrogen gas, but how I'm going to work out the moles of electrons from that? Well, by looking at the electrochemical series, there's a couple of different equations which I can use, which involve hydrogen gas. I'm going to pick one of them. They both give you the same result, however. So I'm going to pick H2 gas plus 2OH minus aqueous goes to 2H2O gas plus 2E minus. As I said, there is another equation within the electrochemical series. I'm choosing to use this one. Ultimately, it doesn't matter. We can see that my hydrogen gas has a 1 to 2 ratio with the electrons, and that means there's going to be twice as many moles of electrons as there are moles of hydrogen gas. So therefore, moles of electrons equals 2 times 1.00 by 10 to the minus 5. And from that I can work out Q equals 2.00 by 10 to the minus 5 times my 96,500. And that gives me 1.93 coulombs. Now the last step that I'm working with is to work out the time. It states within the question that it's per second of operation, and that means my time is simply going to be 1, as within this equation the units for time must be seconds. So that means I equals 1.93 coulombs divided by 1 second, and that is 1.93 amps. Answer C. A lot of students ended up picking the 3.86, and that was because they didn't identify that there was this 1 to 2 ratio between the hydrogen gas and the electrons. Moving on to question 30. A lot of text and a big picture here. Again, some more text. The question asked, which of the following could not be a possible explanation for the lower experimental result? So going back and reading the question, they found that the percentage by mass of copper in the copper oxide was 76.42%. The theoretical yield was 79.86. So we're trying to work out why would this potentially be lower than the theoretical value. And then what we're actually trying to do is find the opposite. Find what could not be a reason for this occurring. So we're going to have to go through all those available options and really knuckle out why this would be possible. So for A, it's saying the copper 2 oxide, which is black, was contaminated with some carbon. Now we need to really go back to this question and understand what's happening here. So we've got an experiment. We've got gas entering this sample unit here, entering this apparatus, and we can see that there's strong heating, a black CuO powder, and the gas is being burnt off. We've got a redox reaction here, and we've got additional gas passing through, preventing the copper from reoxidizing to copper oxide. We're going to have to go through this on a case-by-case basis, guys. And if we consider option A here, if the copper oxide was contaminated with carbon, as this question states, then what would actually occur is that the high temperatures of this reaction, as it states, it's at quite a high temperature. We've got strong heating by a Bunsen burner. At these high temperatures, carbon would actually act as a reductant. And because of that, it'd be oxidized to CO rather than CO2. And according to the equation for that, CS plus CuOS goes to CuS plus COG. This would actually produce a larger decrease in mass of the sample and a lower mass of copper remaining. And this would overall lead to a higher than true value calculated of the percentage copper, a lower than true calculated percentage copper in the copper oxide sample. Going to option B, I'm not going to run through all of them. So option B, it states that some copper oxide remained unreacted when heating was stopped. If this was the case, the copper oxide has a higher molar mass than the copper, so unreacted copper oxide will have a higher mass of copper remaining and lead to a higher than true calculated value of the percentage copper in the copper oxide. That's what we're looking for. That's not a possible explanation. So the answer is question B. This certainly was a little bit tricky and took a bit of time to look through. If you look through the other two examples, they also have reasons why they're incorrect and why it would actually lead to a lower potential value and not why it wouldn't be possible. Great, guys. I hope that helped you out. Thanks for watching. I'm Jesse, and this was another VCE 2014 chemistry exam walkthrough episode. See you next episode.